So parallel lines is an example of a special system of equation. And that's where there's nothing that they have in common. So we found out that when we graphed them, those parallel lines had no intersecting point. And that's what you would call a no solution. So here's a scenario that we would work with. If they gave us a set of equations, our first step is still always going to be to get them into that y-intercept form. So this one's okay. I have to work through this top equation. So my first step would be to do plus 6x to get rid of it, and plus 6x. And then now I would divide by a positive 3. Divide by positive 3, divide by positive 3. So now when I rewrite this, I have y by itself equals, I need to have my x first, just because if I'm going to graph it, that's the way that it has to be. So 6 divided by 3 would give me 2x. And then 18 divided by 3 would give me plus 6. Okay, so if I were to look at this algebraically, like we did in our most recent lesson, that's where I would write these out equal to each other. So if I were to look at them, I have 2x minus 2 is equal to 2x plus 6. And we notice that when we look at our x's, they're exactly the same. So remember back in chapter 1, we did work with these already. It's just that we didn't see them on a graph. We didn't think of them as systems of equation. And now you're understanding that ultimately we are going to see them as a system of equation. Now, normally you would say, okay, get your x's to the other side. It would be minus 2 minus 2x. They cancel each other out. So anytime you see the exact same slope, they have to both be positive or both be negative. And the numbers in front of the x have to be the same. That means they're going to cancel each other out. So now I can focus on just these two numbers. Negative 2 equal to 6. Is negative 2 equal to 6? No. Then that's when we would say back in chapter 1, this was a no solution. Okay, so when you want to see these like visually, okay, if I were to graph these out, this is what it would look like. And I'm going to erase this just so it's not on the graph. If I were to graph out these two equations, the first one I would go to negative 2, and I would go up 2 over 1, up 2 over 1, up 2 over 1, just so you can see my dots. Okay, then if I do the second equation, I would start at positive 6, and I would still go up 2 over 1, up 2 over 1. You can see, whoops, and I went over 2. You can see that if I were to draw the lines, they're going to be parallel to each other. And my lines aren't perfect, but you can see that they're never going to run into each other. They don't have that common point that we worked on back in section 2.5 when we would see the graphs. There's nothing that they have in common. So once again, if it's parallel, there's no point where they intersect, so it would be considered a no solution. Oops, O-U-T-I-O-N. Okay. So we're going to go ahead and look at another one, another sample of something that is a special equation, and that's when we would have an infinite set of solutions. So once again, our first step would be to get it into the y equals format. So this first one's okay, because it already says y equals. We have to work through this one to get it to say y equals. So we would say plus x, which is the same as 1x. So plus 1x, which I like to see it there, because if there's a number with our y, I know I'm going to be doing dividing. So now I would divide by positive 6 to get rid of it. Divide by positive 6, divide by positive 6. So now I end up, and I'm going to write it up above here, with y equals, put my x first. So I have a positive 1/6 x. And then this would change into 30 divided by 6 would be a positive 5. Okay, so now, if I were to write this out algebraically, I would take the back ends and write them out equal to each other. And I know it's hard to see that red. So I would write it out as 1/6 x plus 5 is equal to 1/6 x plus 5. So what are we noticing about both halves? Well, we see that the x's are the same. So it has to be a special equation because those are going to cancel each other out. If I were to subtract it out and do the steps, 1/6 minus 1/6 is 0. I am left with 5 is equal to 5. Well, that's where we call that back in chapter 1, we called it an infinite solution. Okay, I believe up in high school algebra, instead of using infinite, they call it the identity. But our book calls it infinite solution because there's an unlimited number of solutions that would work for this. So if we were to graph these out, just so visually you can see what it looks like, in case you ever come across a visual representation, this is what it would look like visually. So if I take my two equations that I have up there, well, I would start at +5, put my dot, and then I would go up 1 and over 6, which is right there. Okay, so there's my first equation, and if I want to draw the line, I could. But when I go to do my second equation right here, I would start at +5, and I would go up 1 over 6. Do you see how our lines are actually falling on top of each other? If I would have drawn my red line, which I'll go ahead and do, just so you can act like that's a beautiful straight line. There's my red line, and then I went ahead and did the same thing with my blue line and connected my dots. It's actually, they fall on top of each other. So we end up with the exact same line. And you could see that visually when you looked at the algebraic equation, they were exactly the same on both sides of the equal sign. These two equations right here are exactly the same. Okay, so that's what you would call an infinite solution. Okay, so we're gonna go ahead and practice a few of these. So we can work through to solve them algebraically is what we're gonna do. If you're a visual person and you would like to work through on a graph, you may, but unfortunately you're not always going to have a graph. So it's good to kind of get used to seeing it. And not only that, but algebraically, once we get it into that equation, you guys have already done that back in chapter 1. Okay, so my first step is going to be to work to get these into the y-intercept form. So this one's okay. I have to work this one out. So I'm going to just write it down here. So I've got space to write. So I have this equation and I want to work to get y by itself. So I need to get rid of my x. So -1x, -1x. And then I need to divide, and I have to remember that negative's with the 2. So take the negative with it. Okay, so my new equation is y equals, I'm going to put my x first just in case I want to graph it. 2 negatives make it a +1/2 x. And then 2 negatives make this a positive. 8 divided by 2 is 4, so +4. Okay, so that's the first equation. The second equation was this one right here. So when I write them out algebraically, this is what I have. 1/2 x plus 4 equals 1/2 x plus 4. So when I look at them, the slopes are exactly the same. They're gone. I'm left with 4 equals 4. And back in chapter 1, that's what we would call an infinite solution. They were exactly the same. Identity, the number kept its identity. When you're up in high school algebra, it's just the terminology is slightly different. So this would be an infinite solution. This would be on a graph where your line is over your line. And you end up with them on the exact same points. Okay, so let's try another one. Let's try this one. So we have the second equation's already done for us. So we have to work to get that first equation so that it says y equals. So we've got 6x minus 2y equals -2. Okay, so we want to get that 6x out of there. So -6x and -6x. And sometimes you're still going to get a solution, and that's what we're going to practice. Now I would divide by -2. Divide by -2, divide by -2. So now when I rewrite it, I want the x first. So y equals 2 negatives make it a positive. 6 divided by 2 is 3. X. And then 2 negatives make it a positive. 2 divided by 2 is 1, so +1. Okay, my other equation was right here. So I'm going to write that below just so I can see them. Y equals 3x minus 4. So here, I could take the time to go ahead and write them out, but I'm noticing right away, without having to write them out as equal to each other, what do we notice about our slopes? Now that they're in the exact same setup, they're the same, which is going to leave me, if I were to write it out algebraically, it's going to leave me with a 1 on one side and a -4 on the other side. So if I compare those, Do they have it? Are they the same? No. That would be a no solution. Okay, if I were to graph this out, we would end up with those parallel lines where they're parallel to each other. They both have different starting points, but they have the exact same slope, which means the lines are going to be the same. They're just going to start at a different point of the graph. Okay, so if as you're writing these out, you're noticing that your slopes are the same like it was here, you don't even have to go into that algebraic step if you don't feel that you need to. Whoops. Okay, so once again, let's go ahead and work to get our y's by itself. So on both of these, we have to do that to both equations. So our first one, we'll go ahead and just kind of work it out up here. I would do minus 1x, and then remember, when there's that negative, you have to take it with that. So divide by -4, divide by -4, divide by -4. Okay, so when I write out this first equation, I have y equals, my x needs to go first. So here's my x set. Two negatives make it a positive, 1/4x. And then here's my back end, which was 3 divided by 4 is 0.75 if you want to do it that way, negative 0.75. If you want to leave it as a fraction, you could. We'll write it out as a decimal, so negative 0.75. Once again, you could leave it as 3/4 there. We aren't used to having it like that. If we were to graph this one, we haven't worked with graphing decimals. It's doable, but we haven't done that. Okay, so now if I work through the second equation, okay, we would go ahead and plus 3x. So back here plus, I'll change that color, 3x. And then we would divide by 12, divide by 12, divide by 12. Okay, so when I go through, I have to write my x first. So y equals, we're going to get a positive because both of them were positive, but we need to reduce that down. So 3 would go into 3 once and into 12 4 times with an x. And then when we go ahead and do that one, it's going to be a negative. And that would reduce to 3/4, or I could do 9 divided by 12. It's still going to give me 0.75. Okay, so when I look at these, my x's are the same. My y's are the same. What do I have when I end up algebraically with 0.75 negative is equal to negative 0.75? They're the same. That would be an infinite solution. That's where we would end up with both of our lines in the same spot. All right, so let's try one more. What would we do on something like this if we had y equals 3x and y equals negative 2x? Okay, so let's graph it out. Let's visually look at it and see what it looks like. Do you guys remember when we have nothing in the back, it's like plus 0? And I know you can't see that other 0 very well. Okay, so when I do these, well, we're starting both of them at 0, but the slopes aren't the same. So on this one, I know that granted the back end, that y-intercept is the same, but if I graph this out, you're going to see right away that they're not going to be the same. So if I go through and graph it out, they're both going to start at 0. So I'll do this as my red one. But then my slope would be positive 3, so up 3 over 1, up 3 over 1, up 3 over 1, and it would continue. Okay, so there's my, whoops, and I still went over 2. I do that every once in a while. Okay, so there's my line for the first one. My second one would look like this. We would start here, but then I would go through and go down 2 over 1, down 2 over 1, up 2 over 1. So you'll notice that they intersect here. So what I want you to remember is just because right now we're working with those special equations, it doesn't mean all of your answers are going to be no solution and all of your answers are no solution or infinite. Sometimes you're going to get a solution. My solution to this one is they intersect at 0, 0. So sometimes you will get that, and you can compare. If these are not the same, then you're going to get a solution. If your x's are not the same, you're going to get a solution. It's only when the x's are the same that it is a special equation. So that's pretty much it for this part of the lesson. Working special equations, remembering when your slopes are the same, it's either an infinite if your y-intercepts are different, are also the same, or it's a no solution if your y-intercepts are different. Good luck with this one.